So the presentation I put together, I'm starting off with a bit of background information. I'll try and give you a bit of rationale for measuring and managing greenhouse gas emissions. And then I'll discuss why the particular focus on methane emissions. Touch on a few of the related international standards and initiatives that relate to the oil and gas industry and greenhouse gas emissions. Point to some of the useful references or places where you can find useful references on monitoring and control technologies for the key emission sources in the oil and gas sector. And I'll also give you an example of some of the current methane regulations that exist. In Canada, we've got a set of methane regulations that have been in effect for a couple of years now, and they're being phased in. The last aspects of these regulations will be in effect, well, they became effective this year. So these are things that industry is having to cope with here in Canada. And I think it just provides useful perspective to see what's happening in other countries. What we implemented in Canada was very similar to what the US was proposing to implement before the Trump administration came into power. When they came in, I'm sure a lot of you recall, they moved away from climate change. Now the Biden administration, they're back, focused on climate change issues, and they're in the process of implementing their own methane regulations, which will be very similar to what we've got in Canada, but at least it's useful to see what those regulations look like. I will go through some of the measurement techniques that exist for quantifying emissions, but also look at some of the strategies that are related to that in terms of trying to identify regional and local hotspots, use of road monitoring, and finally the direct measurements that people would potentially perform once you're on site at the individual point source level. And then I'll briefly discuss a little bit about methane and greenhouse gas mitigation strategies and the basic process for developing mitigation projects. So in terms of why people would want to measure and mitigate greenhouse gas emissions, I think the reasons depend on your circumstances, whether you're industry or government. Also, they depend on where you are in the evolution of trying to respond to climate change issues and the NDCs that your particular jurisdiction is committed to. Historically, a lot of industry saw that doing environmental work as being the cost of doing business. Often they simply looked at doing the regulatory minimum. But what's changing now is that the regulations are becoming more stringent, especially with respect to greenhouse gas emissions. And there's a lot more clear drivers as to why you would potentially want to go beyond doing simply the regulatory minimum. One of the first things that at least some of the more proactive and larger companies like to understand is what are their risks. So prior to new regulations coming in, a lot of them historically have sponsored studies to look at where their emissions are occurring, what some of the opportunities might be to address those emissions, and how they see that as being a risk to their operation. So certainly, if you look at some of the larger IOCs, some of them have moved away from their more carbon-intensive operations and have divested those assets and have focused on a greener path. But there's also a lot of international attention being given to some of the larger IOCs. And a classical case is what happened to Shell back in 2021, where a Dutch court ordered Shell to reduce its carbon emissions at a faster rate than it was proposing to. So they required Shell to reduce by 45% from its 2019 baseline by the year 2030. And internationally, that has set a bit of a benchmark for other companies. So there's concern that similar lawsuits might be launched against other larger companies. So understanding where you sit, what your obligations are, what your ability to reduce your emissions are. Those are all reasons why people would start to want to look at their own operations and how they could address some of these requirements as the regulations come into force. Identifying opportunities. So in recent years, we've seen some fairly significant increases in the value of natural gas and the value of crude oil, and by implication, the value of liquids that you can extract from natural gas streams. And all of these are creating opportunities that during the initial stages of energy development, companies may have overlooked because they didn't see them as being particularly attractive relative to the core opportunity they were advancing. So normally it's the oil side that tends to be the most profitable, and the gas is often seen as a byproduct. Certainly now there's opportunity to go back and revisit some of those cases and see where some of those gas conservation projects that may not have been economic in the beginning now perhaps are more economic and worth considering. ESG, environment, social, and governance. These are expectations that civil society and the financial markets are expecting of industry. So it's not just the oil and gas industry. This really applies to all industries, but it's becoming very important for companies to be able to demonstrate that they've got good ESG policies and are taking real actions to enforce those policies. And there's mechanisms for reporting out your scorecard in the area of ESG. And that's one of the first things that international lending institutions and the financial markets are now looking at when they consider lending money to companies. So it's something that companies need to consider if they're trying to access the capital markets to advance projects that they may have. Positive relationships with local residents. I've seen this in some of the jurisdictions that we've been working in. The oil and gas companies are being blamed for brownouts that occur in their area because they're users of electricity to run pumps and to sometimes run compressors and other process equipment. So when the local residents see their power go out, they often blame the oil and gas sector on that. And in Colombia, for example, Ecopetrol, the national oil company there, was seeing a lot of vandalism in some areas where the residents were upset about the oil and gas companies being there and being active in their farming areas. So trying to maintain good relations with the residents is important, and it has a direct benefit in terms of maintaining your operations in a sustainable manner and keeping them reliable and avoiding the cost of vandalism. Energy marketability in an increasingly carbon constrained and emissions intensity global economy is something that is also of consideration. So if you look at EU, they're currently in the process of enforcing a carbon border adjustment mechanism to apply duties or tariffs to products that are being brought in, and currently is including cement and some electricity. But the basic concept is that they are paying attention to the energy intensity of the products they're buying, and that actually extends to things like natural gas and crude oil and refined products. So there's, in that regard, fuel quality directives that are being developed to consider the life cycle greenhouse gas intensity of transport fuels. That's something that's being done not just in EU, but in Canada and the United States and other parts of the world. So if you're an exporter of energy and you want to sell into those markets, it's becoming much more important for you to be able to report out what your greenhouse gas emissions really are and do it in a credible, verifiable manner that the international community accepts and believes. And then there's also the potential to obtain market-based rewards. So in some countries at least, and I haven't seen it as much in Nigeria, but there's when you look at the food market, there's a strong market for organically grown products. And in the oil and gas industry, there's an emerging market for green oil and green natural gas. And so what does that really mean? It means if you're producing oil or you're producing natural gas, that from the point of origin, the wells to the market, that path that the production takes, if the total emissions intensity of getting the product from the source to the marketplace is low relative to international norms, then the difference between your intensity and those norms or benchmark values is a basis for generating what are called performance credits. And there are platforms where if you're able to demonstrate that you've got green production, you can provide the information that's needed to develop those credits, and then they're marketed through a blockchain system that tracks all the attributes related to your credits, so that people can see the detail and understand exactly where the information came from and have confidence in what's being produced. The buyers of those typically are utility companies that are trying to demonstrate that they're keeping their emission intensities low. But there is a real market for it. It's an emerging market. There's one of the platforms that is marketing these types of credits is operated by a company called Expansive. If you Google that, you'll come across their platform, and you can read up more about what's involved in trying to market or generate performance credits in that market. Why the focus on methane? If you've been following greenhouse gas emissions for any time, you'll realize and see in the literature that there's a huge focus on trying to reduce methane right now. And it's not that CO2 reductions aren't important. Anything that is cost effective and provides material reductions in greenhouse gas emissions, whether it's methane, CO2, or nitrous oxide, is important to do. But there's particular value in focusing in on methane. Methane is a powerful, short-lived climate pollutant. Its lifetime in the atmosphere is 12.4 years, based on the latest data published in the IPCC Fifth Assessment Report. The actual lifetime in the atmosphere of methane is a number that has varied over the years, and it's something that the climatologists and researchers are spending a reasonable amount of time studying. The initial values that came out a few years ago were more like 11 years, but now it's up to 12.4, which is why in the literature the global warming potential for methane has been increasing from assessment report to assessment report. Methane is responsible for approximately 30% of the global temperature rise to date. While it's a lot less abundant in the atmosphere than CO2, on a mass basis, it's 28 times more potent than CO2 over a 100-year time horizon. So if you look at the graph I've got on the right-hand side, and you look at that brownish colored curve, that shows you what the absolute global warming potential of methane is. So it starts off at 0 when it's first released, but you see it rapidly rises, and then it hits a plateau. And the plateau is where you've reached the 12-year life expectancy of the methane in the atmosphere, and then it stays unchanged. You've created a certain amount of radiative forcing, and that stays constant from that point onwards. If you look at that global warming potential relative to the global warming potential of carbon dioxide, then you get this 28, or this factor of 28. So that would be over a 100-year time horizon. So if you were to go from 100 up to this curve and come across, that would bring you to roughly 28 on the y-axis. If you were to go to 20 years and come up and go across, that would bring you to roughly 80 on the y-axis. If you go to a shorter time period, then the number is even higher. And so the implication of that is that for every ton of methane you reduce, in the short term, it's like reducing at least 80 tons of CO2. So you get this leveraging effect. It makes it much more practical to go after methane than it does to go after CO2, provided the opportunities to reduce it are practical. The other factor is that methane is a marketable commodity. Depending on the jurisdiction you're in, the value of methane can be somewhere between $2 and $17 a gigajoule when you get it to the marketplace. The $2 value is what we see in North America right now. The $17 value is more of what would be seen in Asia and in Europe at this point. So targeting methane can achieve significant cost-effective near-term emission reductions in CO2e, which is why people are so focused on it right now. Some of the secondary benefits of going after methane in particular are it's a conservation of a natural resource that's not renewable. It promotes improved workplace safety and improved local air quality through reduced emissions of co-pollutants, such as criteria air contaminants. That would be things like carbon monoxide, sulfur dioxide, NOx, VOCs, PM2.5, and air toxics. In addressing the opportunities, it creates local job opportunities for people that live near oil and gas facilities, and it provides potentially improved access to electric power, resulting in increased quality of life. There's a very strong correlation between a person's access to electric power and the quality of their life. With electric power comes lighting and schools and hospitals and the ability to create manufacturing operations. There's a whole, well, there's a lot of information that's shown many times that when you provide clean energy and electricity in particular to impoverished areas, it has a big impact on helping them to rise above that and improve their quality of life. So not just trying to benefit the whole world, like the impact of climate change on the whole world, which is a global issue, but looking after some of these things actually have a local benefit and are important to consider in your own economies. So what are some of the related standards and initiatives that exist for methane? Right now, there's a strong political move to get countries to sign on to the global methane pledge. This pledge commits countries to move towards using higher tier IPCC good practice inventory methodologies, and it also commits them to take voluntary actions to contribute to a collective effort to reduce global methane emissions by at least 30% from 2020 levels by the year 2030. Reducing methane emissions from oil and gas operations is seen as being among the most cost-effective and impactful actions that governments can take to achieve global climate goals. It provides, the global methane pledge provides policy toolkits to the signatories. It provides access to selected technical resources that includes things like relevant technical reports, best practice guides, and methane estimation tools. And it also provides links to related initiatives such as the Global Methane Initiative, the Global Gas Flaring Reduction Partnership, and the Climate and Clean Air Coalition. Currently, there's 150 countries that have joined the Global Methane Pledge. Nigeria is one of those. There's approximately 195 countries in the world right now, so that's 75% of the jurisdictions have signed up for it. Of the ones that haven't, most of those would be countries that really don't have much of an oil and gas industry, so they don't have the same opportunities. But it's impressive that there's 150 countries that have signed up to it. In looking at what are some of the international standards that might apply, the key standard for at least quantifying methane emissions from, well, at a project level, at a company level, at a national level, is ISO standard 14064. And this standard has three parts to it. The first part is how to conduct a greenhouse gas inventory, how you establish your boundaries, what you include in that, what are the direct contributors and what are the indirect contributors. It also provides the procedures that you would follow to establish project-based reporting of emission reductions. And so what are the well, issues like project leakage or indirect emission contributions that might occur outside of the project boundary, or matters that are addressed there. And it also provides a standardized process for verification of a greenhouse gas inventory. So anyone who's involved in developing inventories or developing greenhouse gas projects or verifying these sorts of things should have gone through some training on ISO 14064. The Oil and Gas Methane Partnership is an initiative that was created by the United Nations Environmental Program specifically for the oil and gas sector, and it establishes a measurement-based international reporting framework that companies can use to report out their emissions and their emission reductions and details of their mitigation programs. Currently, there's over 100 companies that represent 35% of the global oil and gas production, over 70% of the LNG flows, and nearly 25% of the global natural gas transmission and distribution pipelines that have signed up to the OGMP 2.0 initiative. That initiative identifies 13 different key sources in the oil and gas sector that it provides both guidance for how to report out the emissions from those sources, but also provides guidance on how to quantify those emissions, and points you to some information on the mitigation measures that are available to reduce each of those types of source or emissions from each of those types of source categories. There's 5 levels of reporting under that initiative. Level 1 is reporting out emissions by a region or a country, where you provide a single number for that whole region. That would be analogous to performing a tier 1 approach under the IPCC, where you're providing a very high level assessment of your emissions. There's not a lot of transparency or detail, and the expected uncertainty in those kinds of numbers is very high. Level 2 is reporting out those emissions on a consolidated basis, but for specific source categories. So how much from fuel combustion, how much from venting, and how much from flaring, for example. But just giving a single number, again, by jurisdiction for those individual categories. Level 3 would be providing more detailed bottom-up type assessments of those emissions and using generic emission factors from the literature. Level 4 would be developing source specific emission factors based on your own measurements and using actual activity values to drive those, and coming up with a detailed bottom-up assessment of your emissions that is largely a function of measurements and in some cases the use of process simulators and fairly refined methods for assessing your emissions. Level 5, which would be the highest level of reporting, would involve doing a level 4 assessment, but including calculations on the uncertainty in those estimates and providing additional site level measurements to reconcile some of the source level inventory. So that would be, for example, doing remote monitoring to help verify the numbers that are coming out of your assessment for a facility align with what you're actually seeing downwind of that facility, or based on satellite data. So it's not specific about what you need to use to do the verifying measurements, but it could be doing road-based monitoring, it could be doing aerial surveys, it could be doing satellite-based measurements. There are there's also, through the Climate and Clean Air Coalition, back in 2017, they took a lot of the information that was available from the US EPA's Gas Star program on lessons learned and successful mitigation strategies for different types of control options or different types of emission sources in the oil and gas sector, and they put together a 9-volume series that reviewed how to measure those emissions and how to mitigate those emissions. So they're still relevant documents. They're still available on the website. You have to dig a little bit to try and find them, but I captured a screen image yesterday from going onto the CCAC website that shows that if you put in at least the title of the report, you can find these reports on their system. And as I indicated, they were all published in 2017. So if you use their filtering systems, you can eventually get access to those documents. Other useful information, other sources that would apply that aren't accounted for in this 9-volume set would be unit, facility, and pipeline level blowdowns that occur. Other forms of process venting, which would potentially include the release of CO2 emissions removed from produced gas using a gas sweetening unit, as Sunday discussed in his presentation. And then flares. They're a source of incomplete combustion. And there's two types of flaring. There's routine flaring, and that's where, for example, you've got a continuous waste gas stream that you're burning using a flare. And then there's non-routine flaring, and that would be things like process upsets or intentional release events where you're depressurizing equipment or trying to clear a hydrate from a pipeline or those sorts of things. And then there's a third issue, which is the matter of unlit flares. So the DREs, based on recent studies that have been conducted in the US, and the DRE is the destruction removal efficiency of a flare with respect to methane. So recent data suggests that the true value is somewhere on average in the range of 87% to 94%, and not 98%, which is what typically gets used in emission estimates. An interesting study that was done by EDF, the Environmental Defense Fund, in 2022 showed that in the Permian Basin, 1 in 10 flares was actually unlit. And so that made them super emitters. And there's been a number of articles about unlit flares globally that have been picked up by satellites and identified as super emitters that have contributed huge amounts of methane and essentially CO2 equivalent emissions to the atmosphere. Stationary combustion sources are something that are being looked at as well, as Sunday had mentioned in his presentation. Methane slip from incomplete combustion is the concern there. Methane slip should be very small for things like heaters and boilers and for gas turbines, but can be potentially fairly significant for reciprocating engines. And then the last category is accidental releases. Sometimes it's interesting to see what's in the public and in the commercial domain with respect to emissions. If you're an operator for your facilities, if you're a country for your jurisdiction. Currently, IEA, the International Energy Agency, has a tool called Methane Tracker. It's something you can access on the internet and see what emissions are, or what they estimate emissions to be in any jurisdiction. And they're focusing in on the methane emissions. So for Nigeria, they estimated that the methane emissions for the upstream oil and gas sector ranged between 1.83 and 4.79 megatons per year. And the contributions were mostly from venting. As well, the GGFR provides a website that allows you to access information on active flares that exist in countries around the world. So this is information they've developed from satellite monitoring and correlations that they've used to convert the satellite data into estimated flaring rates. And that information is publicly available. And the image to the left here is actually an image that I got off of the GHGSat website. So this is the kind of resolution where their system works well that you can see. So here they're identifying emissions from individual facilities. This happens to be somewhere in the Middle East or North Africa based on the terrain. If you go back to the IEE website, not only do they give you, total emission estimates for jurisdictions, but they also break that down by where those emissions are coming from. So what sector, and if you look at the oil and gas sector, it breaks it down even further in terms of what the sources for that were. And it provides a comparison of what they're estimating versus what you're seeing in other reported inventories for a particular jurisdiction. So in this case, they're comparing the emissions that they've assessed to values that are published by the UNFCCC, which would be the National Communications by Nigeria to the UNFCCC. But it's also showing estimates that have been developed by various research groups, and their numbers are somewhere in the middle. Our experience and it's quite limited because we haven't done it in a lot of countries, but where we've done it, my sense is that the IEA numbers, even though they're kind of middle of the road here, if you look at the graphs on the right-hand side, still tend to be conservative and tend to overstate what the emissions would typically be in a jurisdiction. But again, that's just initial observations based on very limited data set. If you drill down into the oil and gas sector, here's what it says is happening in Nigeria. That most of your emissions are coming from offshore operations, but onshore operations are still fairly significant contributors. And most of that's related to oil production, not the natural gas side, which makes sense. If you're producing natural gas, you're trying to keep that gas in the system and get it to the marketplace. So there should be a lot less emissions from that. But with the oil side, that's where gas often is seen as a byproduct and effectively can be stranded and not necessarily managed in the best way possible. And again, on the right-hand side, you see similar estimates from different groups on what those emission contributions would be, depending on whose estimates you look at. This is just a table that shows what the emissions from different countries are, and it shows it as a function of the year and shows what the most recent change in those emissions are. At one point, Nigeria was much higher up on this list, but right now it's sitting at what is that, position 7, so the 7th ranked emitter of methane emissions. And IEA also provides a marginal abatement cost curve. So it looks at different technologies that can be applied in the oil and gas sector. These would be essentially all the technologies that the CCAC and the Global Methane Pledge talk about, and OGMP as well. And they're showing that if you, and these types of curves are really hard to look at because they're really dependent on your circumstances, what technologies are going to be cost effective for you and which ones aren't, and what the penetration potential of those technologies will be in your sector. But this is a generic marginal abatement cost curve that is intended to reflect what they believe is the global circumstance. And it shows that there are a reasonable number of opportunities that if they've got a negative value, then those are cost effective to implement, so that you can get quite a large reduction in emissions by simply doing what is cost effective or has a zero cost to reduce those emissions. So that would be basically taking you to here. If you come down, that would give you a 30 megaton reduction in methane emissions. This is the kind of data that's available from the World Bank's GGFR. This is showing the location of flares around the world, and you can zoom in on a particular territory. And so I've done that for Nigeria. So here you can see where they're showing flares, some of them offshore, some of them onshore, and you can actually get a listing of the emission rates or the flaring rates for each of these flares from their website as well. Methane regulations. So the methane regulations in Canada, as I mentioned earlier, are currently, I think, the only set of regulations that have been fully put into force and are what would probably be deemed fairly onerous requirements for industry. They're targeting to achieve a 40 to 45% reduction in methane emissions from the oil and gas sector in Canada relative to 2012 levels by the year 2025. Those requirements first came into effect in January of 2020 and have been phased in since then. And the last remaining requirements under these regulations became effective January 1st of this year. Based on what they're seeing in terms of how industries have responded to this and the reductions that they're able to verify are occurring, they're wanting to further reduce those, or they're wanting to implement even more stringent requirements. So sometime this year, they're coming out with a draft set of regulations, and those new regulations are expected to target a 75% reduction below 2012 values by the year, or so that should be 2030, not 2020. Anyways, I will show you what those requirements actually look like. So for fugitive equipment leaks, they're requiring that companies do an LDAR survey at their facilities 3 times a year. And you might ask, why 3 times? Why not just quarterly? And the reason for that is in Canada during the wintertime, with the cold temperatures, it's hard to use some of the leak detection equipment. It just simply doesn't perform that well. You need good contrast. If you're using optical gas imaging cameras, which most people are using these days, they simply don't work that well in the wintertime. So you don't get good detection capabilities, and some of the facilities are actually harder to access in the wintertime than they would be in the summertime. Interestingly, I see some of the same issues in tropical environments. There's usually a rainy season, and during the rainy season, there's a lot of cloud cover and a lot of rainy days. And during that time of the year, it's equally challenging if you're using an OGI. They, again, need proper contrast. The best time to be using them is on a bright sunny day, and if you don't have that, then it can be very difficult to see leaks. I've been using a camera on those types of, or in those types of circumstances, and it's quite dramatic. You can be walking around a piece of equipment and not see anything, and then suddenly there's something in the background that provides that contrast, and for a very short part of your circling of that source, there's a place where you can actually see the emissions. Otherwise, you're totally blind to it. So it makes sense that you wouldn't force it to happen every season of the year. You'd only force it to happen when it would be practical to apply. There's also, and those requirements aren't just monitoring for leaks and tagging them. There's specific requirements that if you find a leak, they have to be repaired within 14 days. And if you can't repair it, then you have to schedule it for the next available shutdown. And if the leak rate from that source is high enough that you would incur more emissions by waiting until the next shutdown than you would if you force that shutdown now, then they require you to force that shutdown now. So it tries to be practical in terms of what will achieve the minimum amount of emissions. On compressors, they require companies to measure their emissions from the seal vents on their compressors. And currently the requirement is that they do that annually. They have to report those numbers back, and they have to show that their emissions are below certain performance targets that they've set depending on the size of the compressor and and the type of compressor. Venting from well completions involving hydraulic fracturing. So now they're saying that there can't be any venting. You need to use flaring, and where possible, you need to be using what are called clean completion. So that's where you're actually not venting or flaring. You're producing into gathering systems that have already been established that you can use to capture the gas from the flow back of liquids that occur during the flow back of liquids from a hydraulic fracturing event. Facility level production venting, they're setting limits of, or they have set limits of 1,250 cubic meters of gas per month, or 15,000 cubic meters per gas per year. So everything from pneumatics to glycol dehydrators, everything that's on site cannot exceed that amount of venting. If there is an exceedance of that amount of venting, then you have to put some sort of a control measure in place to deal with it. And that could be flaring, could be capturing some of that gas and using it as fuel, could be using incinerators. And there's also requirements to limit venting from pneumatic devices. So they've got a limit of 0.17 cubic meters of natural gas per hour for pneumatic controllers. And a lot of companies have gone to convert their pneumatic controllers from high bleed to low bleed or no bleed, or else they put in air compressors to provide compressed air as a supply medium instead of using natural gas. Measurement techniques. This basically summarizes the types of approaches that can be used. Point source measurements, so that's where you're going in directly performing a measurement on the source. This is useful information because ultimately to address an opportunity, you need to understand what the cause is and what the actual emissions from that source are to drive potential economics on it. The problem with it is, and it's, of course, is also the most accurate approach for doing these things. Typically, you'd expect an accuracy of plus or minus 10% on direct measurements, or even better. The problem with it is it's time consuming, and it means that you need to look at a lot of the facility to try and identify these sources. Aerial surveys can be done to help identify facilities that are high emitting facilities where you might want to target your efforts, but they can also be used to help zero in on hotspots on a particular facility if it's a larger facility. These can be time consuming and expensive to conduct. A road survey is where you have a vehicle mounted monitoring system. You drive downwind of the facility and you can use that information to get a snapshot of what the emissions need to be. This table I'm actually presenting came from one of the websites that I was looking at. So its comments here about there needing to be post-survey calculations isn't quite right. We've actually developed a mobile monitoring system or a road-based survey system that we've been using that actually geolocates the source of the emissions in addition to detecting the emissions, and it also quantifies the amount of those emissions, and it does it in near real time. So you can see some of this as you're driving the vehicle, but when you've completed your runs on a particular identified source, it can be generated in the field, the actual emission estimates. Satellites are similar. They are able to provide the ability to identify regional and local hotspots and even identify a specific part of the facility where emissions are coming from. The issue with the satellites is they're, of course, the least accurate in terms of being able to quantify emissions. And they have some limitations. They don't really work very well at northern latitudes. They aren't able to, or they're simply not as sensitive and don't have the detection capabilities that you would really want at northern latitudes. They work really well in the in North Africa and the Middle East, and that strip all the way around, all the way around the world. So there are places where it works very well, but still there's questions about how accurate the numbers really are. And then along the bottom of the image here, I've shown what the typical expected accuracies of these are. If you're using optical gas imaging cameras, they have a quantification capability where it looks at the intensity of the emissions plume it sees and the movement of that plume, and make some estimates as to what the emission rate would be. And those under good operating conditions would typically be plus or minus 40% uncertainty. The aerial surveys typically are plus or minus 50% uncertainty, and the satellites are, like I say, it's questionable what the accuracies of those really are. In terms of satellite monitoring, you can track, there's methane-specific satellites that exist that can track methane on a global scale, but can't detect small-scale sources, which are responsible for a lot of the total methane emissions from the oil and gas sector. Others can provide excellent data for known sites, but can't see beyond small areas. And existing satellites don't provide measurements over equatorial regions, northern areas, or are very challenged, at least for offshore operations and are affected by cloud cover. Sentinel-5P is a methane satellite that was launched by the European Space Agency. It's got a resolution of 5 kilometers by 7 kilometers. The data from that are publicly available. You can download it and graph it and look at where hotspots are across the country. GHGSat offers a resolution of 50 meters by 50 meters, so much more resolved. The Italian space agencies launched a satellite that offers even better resolution, 30 meters by 30 meters. NASA has a geocarb satellite that provides or tracks sources and movements of methane around the globe. And the Environmental Defense Fund is proposing to launch a satellite in early 2024, which it says will be the state of the art at the time it goes up, and will be able to identify and quantify emissions from sources larger than 500 kilograms per hour. This shows an image of at least the mobile monitoring system that we've been using. Typically, we obtain an SUV and mount a wind anemometer on the roof to track wind conditions relative to the vehicle, and it has a GPS that tracks the vehicle movement relative to the ground, and then you can back out the vehicle movement from the wind data and get wind speeds and direction relative to the stationary ground as well. And inside there's analyzers that process the gas that it's seeing as it drives along, or the ambient air that it sees along as it's driving along the road. The primary capabilities are the ability to detect and quantify methane emissions from point, line, area, and volume sources. It works, or based on controlled releases that we've done, it works quite well if you've got reasonable wind conditions. So we're seeing typically accuracies in the range of plus or minus 25% under stable wind conditions and speeds of 2 meters per second or greater. If you're getting a wind that meanders, then it affects your ability to properly geolocate the origin of the source. And if you're getting gusting winds, then it affects your ability to get an accurate quantification of that emission rate. And where we do get numbers, what we're seeing is a slight negative trend in our data, which I see as a positive thing, because we're erring on, at least in terms of trying to identify mitigation opportunities, we're erring on the side of conservatism. It does geolocate, the origin of the source it detects, and it does that by assuming that the source is a point source. If it is a point source, it tends to be, that would be furthest away. If it was an area or a volume source or a line source, then those would tend to be closer in to produce the same Gaussian plume distribution that you would see at the point you drive through the plume. Fingerprinting, we not only use methane, but we have the potential to monitor for ethane and actually quite a large variety of other compounds. And that can be used if you're looking at a large facility to help fingerprint where the emissions, where those emissions are actually coming from within a facility. The results are overlaid on Google Earth and Google Map images that show you some of the key features of the facility that you're looking at. We do have the option to invoke the use of a UAV to get more, well, to get higher resolution images that you would overlay your results on, so you get better clarity on what the sources might be of the emissions that you're detecting. And it provides real-time graphics and streaming that allow you to do reporting in the field, and it's easily deployable. Everything breaks down into several cases of luggage that can be taken on a commercial airline and flown to different parts of the country or flown to different parts of the world. The advantages are that it provides real-time monitoring and in-field data analysis. It's able to cost effectively and quickly screen many facilities or sources and rank order them based on their assessed emissions. It detects emissions that on-site screening methods miss. We, in a recent study, worked in parallel with a team that went on site and did direct measurements, and they used optical gas imaging cameras to detect leaks. And what we found was the best strategy was to screen the facility first with the mobile monitoring system to identify the hotspots, and then send the teams in armed with the knowledge of where the sources appear to be located, and they would then pinpoint the source and determine exactly what it was and do their direct measurements on it where that was possible. It is also had the advantage that it was able to quantify emissions from sources that the camera and direct measurement techniques simply couldn't quantify the emissions from. So we didn't miss anything. We always had complete quantification of the emissions from a facility. And as well, it ties in nicely with the OGMP 2.0 level 5 methane reporting verifications. And it actually provides comparable, or in some cases even better, sensitivity than other methods can. Certainly better sensitivity than the aerial techniques would. But even with the OGI camera, there's cases where we could see emissions that the camera couldn't see using the viewing capabilities of the camera. The disadvantages are, of course, we need wind, and we need not just wind, but stable wind conditions to be able to get good results. But even results that suffer from uncertainties because of gusting, we still have the ability to help pinpoint where the emissions are and determine where the hotspots are, which helps to guide ground teams that would be used. It's not as accurate as the direct measurement techniques, and it does require drivable downwind terrain. So it doesn't necessarily have to be a road, but it needs to be at least firm ground that you can drive on, that allows you to get on the downwind side of the facility. The types of sectors that we've targeted using the monitoring system have included oil and gas facilities, both upstream and some fairly large gas processing and LNG facilities. We've also looked at refineries and petrochemical facilities. We've used it in urban areas to identify leakage from gas distribution systems. We've driven through light industrial and commercial areas to identify leakages there. We've used it to quantify emissions from landfills, sewage treatment plants, even agricultural applications, looking at enteric emissions from livestock. And we haven't had an application yet to use it on something like rice paddies or crops that would be methane intensive, but we're in discussions with Agriculture Canada to do some of that kind of testing. And we've also used it to quantify methane emissions from CNG fueling stations. what typically are the biggest opportunities that we see? Certainly in North America, where there's been regulations to try and deal with things like a lot of the routine venting that takes place, where we're seeing large amounts of emissions tends to be from the flares, especially unlit flares, but also venting of flash gas from production storage tanks. And that includes both the produced oil tanks and the produced water storage tanks. The water tanks have some hydrocarbon carryover, and that promotes or is a source of flashing that can be material in some cases, especially where you've got large amounts of produced water. And fugitive equipment leaks still remain a fairly noteworthy source and continue to be an area that is worth targeting. This slide just shows some of the results from the mobile monitoring system. The blue triangle denotes the plume spread as it moves away from the source. So the apex of that triangle is what it's pointing to as being the source. So on the left-hand side, you can see it's pointing at a specific tank, and it's pointing at that tank based on data that we got on the downwind side of this facility. So it didn't see much between the tank and that road that we were driving along, or what it did see blended in with the emissions from the storage tank. And the amount of emissions that we're seeing and able to quantify from that tank were 6.4 cubic meters of methane per hour. So it's not seeing the non-methane contributions that would be coming from that tank, which would increase the value of the mitigation opportunity. If that tank has a lot of heavier hydrocarbons in it, or sort of the vapors coming off that tank have a lot of heavier hydrocarbons in it, then the value of that stream would be even greater than what the reported methane emissions would imply. This is simply another example of where it's picked up. In this case, it was venting emissions from a vent system that went to the edge of the facility. And this was the case where the on-site team was focused on the main process areas and for whatever reason didn't look out at some of the potential sources around the perimeter of the facility and had missed this particular source. And it was a bit larger source, 18.8 cubic meters an hour of methane coming off. But again, it's interesting to see that the system accurately sees it and points to it. Here's a case where we actually use the monitoring system on a ground flare. So this flare is simply burning the purge gas that's being supplied to it and whatever leakage is occurring into that flare system at the time. What's interesting here is that the methane plume and the CO2 plume aren't perfectly commingled. And what that suggests is that part of the ground flare wasn't lit and was contributing some methane emissions, and part of it was lit. And so then you're getting the CO2 emissions coming off that. And when we looked at the numbers from that, it suggested that the DRE for this particular flare was 75.2%. And here's a case where we were looking at, it was a small flare, but what's of interest here is that there's a lot of liftoff. So liftoff is the distance between the tip of the flare and the base of the flame. And if you have a lot of liftoff, then you actually see a lot of lateral emissions of unburned flare gas to the environment through convective mechanisms. So there's a lot of gas that extends out of what we call a cold plume that comes from this particular part of the flare, and there's a separate hot plume that would come out of this. And here, because of the high velocities, you're getting good air entrainment, and it shows that you're getting, based on the coloring of the flame, reasonably good air entrainment and good combustion. So what we saw here is we weren't able to pick up the thermal plume because that would have gone up, but we were able to pick the cold plume coming down, and that shows what the flare looked like as we were driving past it. And the results for it, are shown here. So we could see this methane plume quite well from the that bottom region, and here we were seeing 153 cubic meters per hour of methane being emitted from that flare, completely unburned. Point source measurements. Most of these are really directed at fugitive equipment leaks. Actually, I know I'm running out of time here, so what I'm going to do is just skip over some of the detail here and just show you the basic technique. So under method 21 does allow you to use slope solutions or the bubble test to detect leaks, and they even suggest a means where, based on the rate of bubble formation and the size of the bubbles, you can use that to quantify the leak rate. And method 21 is an approach that was developed by the US EPA originally for application at refineries and chemical plants to detect VOC leakage. But it's also used for detecting methane leakage at upstream oil and gas facilities. And it involves, it's the most labor intensive. It involves someone going around and actually checking each individual component to look for leakage. So if you spray it with the soap solution and it bubbles, then you know there's a leak. If it doesn't, then there isn't a leak. There's also the ability to use a handheld gas detector to do the same measurements. Here you take your probe and you pass it over the potential leakage points, and there's a specific procedure in method 21 that tells you how to use that. And you record a ppm reading, and a lot of the regulations that define what is a leak from a regulatory perspective define it in terms of a ppm screening value. And it's a crude indicator of leakage, but it's a method that can be used to survey components and find out which ones are leaking and obtain an objective decision as to whether or not it needs to be tagged and repaired, or whether it doesn't. So not all components that show measurable VOC readings, or in this case methane readings, using your portable gas detector need to be repaired. They only need to be repaired if they have ppm readings over a certain value. And typically these days that value is 500 ppm. The OGI cameras have the advantage that they're easier to use. You're not having to get as close to the individual components. You don't have to record data. You simply, the procedure there is, if you see leakage from the component, then you need to tag it and repair it. If you don't see leakage with the camera, then of course there's no indication of leakage. It's not a leaker, and you don't repair it. That doesn't mean that there wasn't some nominal amount of emissions occurring. It just wasn't detectable by the camera. And so when people are actually reporting out their emissions, they typically report two things. They report the contribution that they actually detected and measured from sources that were defined as being leakers, and they would do a calculation to estimate what the emissions from what are termed non-leakers would be. And the sum of those two would be what your total emissions for a facility would be. The reason people do that is so that you don't show a zero emissions for any of your facilities, because optically that's difficult for a lot of stakeholders to believe, and in theory isn't really possible. There's no such thing as 100% effective seal or mechanical coupling. You potentially have some level of emissions. It's just a matter of what the detection capabilities of your leak detection method was, and what the regulatory leak definition is that you're applying. This shows the two technologies that are available, or the two manufacturers of optical gas imaging cameras. One's the FLIR, the other is the OpGal. The FLIR is a bit more expensive. It's a bit more ergonomic. It's been available longer. The OpGal is a bit heavier, and but it's cheaper. So they both have fairly good detection capabilities. So technically they're providing the same functionality. They just slight differences between them. I think the FLIR tends to be more popular than the OpGal. We've used both in the field. And this is, if you have not seen the images from a an IR camera. This is what you would see when you're looking through the screen, depending on the mode you've put it into. But this is showing emissions coming from a storage tank. So it doesn't see methane specifically, it sees hydrocarbons. And so when you see a plume like this, it could be all methane, it could be very low methane contributions and very high emissions of non-methane hydrocarbons. And that's what you would see if you simply looked at it with your naked eye or with a digital camera. And this was just emissions coming off a smaller component, but same idea. Here it's leaking from a threaded connection. It's so you can see small sources, you can see larger sources, you can see them close up. The farther away you are from a source, the worse your detection capability would be. Oops. In terms of leak rate measurement equipment, one of the most common pieces of equipment that's used is called a high flow sampler. Here, high flow sampler is being used to measure emissions from seal vent at a compressor station. What's being done here is an extension pole is being used to reach some ducting up into, or flexible hose up into the seal vent, and the actual high flow sampler is what the second person is holding on the railing there. And it basically has an induced draft system. It's like a vacuum cleaner. It, in theory, is capturing all the leakage that's coming from a source. If it's a vent like this, it's a little bit easier to do. If it's a valve, you need to position it so that you're not just, I mean, you're capturing some air from around the valve, but you're capturing, the intent is that you capture all of the vapors that are being, or gases that are being emitted from that valve. And so as long as you're getting 100% capture, then your results are accurate. What the device does is it measures the sampling rate, and it measures the concentration of hydrocarbons in that stream, and then the product of that is your actual emission rate. This is what the high flow sampler looks like. It fits in basically two cases. One case for the instrument itself, which is this device here, and then typically the sample hose and a lot of the accessories would go into a second case. If you're looking at emissions from a pipe or an open-ended line, sometimes you can use a velocity probe to do a measurement. The EPA Method 21 establishes a procedure for doing that, where it defines specific points at which you would perform a measurement. And this is, I mean, all of these instruments need to be intrinsically safe to be able to use in a hazardous location. There's not a lot of vane anemometers, which is what this is, that can be used in a hazardous location, but there are two vendors of that type of technology that have probes that are handheld anemometers that can be used in hazardous locations. This other device is a thermal dispersion anemometer. If you've got a port available on a flare line, for example, you could potentially use this to do measurements. Storage tanks can be very challenging to measure the emissions from. The biggest challenge is getting access to the roof. Here we're using what is it's a vortex gas flow meter. We were using it for two reasons. One, it had a reasonable operating range that covered off what we needed for a typical tank venting application, and it was completely intrinsically safe or rated for use in hazardous locations. So everything from the handheld device to the cabling and the actual probe that's wedded to the gas stream was all suited for a hazardous location. So what it's doing is it's measuring a velocity in the pipe, and based on the diameter of this flow cell, it's capturing or determining what the flow rate is. And you can't see it, but inside is a flow straightener that's being used to straighten the flow before it goes through or goes past the velocity probe to ensure that we got a fully developed flow profile to get improved accuracy in the measurements. This is an ultrasonic transit time gas flow meter that we've been using on wellhead casing vents. And the advantage here is these have very high operating ranges. The turn down ratio, and this is typically 2,000 to 1. often very accurate. It's a little, I mean, it's susceptible, sorry, not susceptible, it's tolerant of there being some particulate matter or some aerosols present in the gas stream. Fairly robust. The only challenge is that it needs to be wetted to the gas stream, which is why we have this flow cell to do that. And again, there's a flow straightener in the upstream section before it goes through that cell. And the disadvantage of this one was that this part of it wasn't rated for use in a hazardous location. I mean, everything else was, but this wasn't. When we use it, we typically put an extra run of tubing on the end to get the emissions to a safe location. And we would be using it in areas, for example, if you're doing it on a wellhead, we would be far enough away that we wouldn't be violating any hazardous area location classifications. Combustion testing to measure a methane slip. Typically, we've been using cavity ring down spectrometers to do that are specific to measuring methane emissions, and as well measuring, we're doing a normal combustion test, also using cavity ring down spectrometers, so measuring carbon monoxide, carbon dioxide, and oxygen levels and CO2 levels and moisture levels in the different gas streams. And knowing that information, you can develop an emission factor. If you develop an emission factor and you know the fuel gas consumption rate, then you can determine what the emission rate for that source is. Sometimes you can measure that flow rate using clamp-on ultrasonic flow meters. Other times you need to look at what the amount of process work the associated device is performing. So whether that's thermal work by a heater, or it's compression work by a compressor, or pumping work by a pump, you know what work is being done to the process, then knowing typical efficiencies for that type of device, you can back calculate what fuel would have been required by the combustion device to meet those requirements. Emissions mitigation, very quickly, this just shows kind of the life cycle of a typical project. Usually you go through a screening process to identify potential opportunities. And you do some preliminary economics on those opportunities based on the gross value of the losses that you're seeing. Then you would do a pre-feasibility assessment and ultimately work towards developing a refined business case that you would present to senior management or to financiers to get the funding for the project. And if you don't have those, then, or funding sources, then you would look to exploring external financing mechanism. This is just a case where it's not a matter of going in and getting a spot measurement of the emissions. Here we were looking at flaring rates, and we were using an inline tracer technique to measure what the instantaneous flare rate was. And then when we designed the solution for it, we looked at what the variability in that flow rate was and what things could be done to smooth that out. But ultimately, understanding how the flow behaves is an important input parameter to your design analysis, and knowing the composition of the stream was also an important input parameter. The types of mitigation technologies depend on a lot of what it is you're looking at, but if you're looking at stranded gas applications or waste gas recover opportunities, the sorts of things you can consider are conventionally would be gas conservation schemes where you collect the gas and tie it into a gas gathering system, displacement of energy purchases, using the gas to run equipment or power equipment and produce electricity, and potentially even generate electricity for offsite sales. Small scale gas to liquids applications are something that a lot of people have been looking at. And there's a number of pilot cases where the technology is actually being applied. Larger scale LNG is an option, but that requires certainly much larger volumes of gas to make it appropriate. There could be hybrid solutions where, for example, you try to recover the condensable hydrocarbons from a waste gas stream, and then what's left over you use to generate electric power to drive the process, or the extraction process, and possibly other needs on site, and what's left over after that could get sold into the grid. If you are recovering condensable hydrocarbons, the options for getting that to market are: one, you could blend it into the weathered crude oil or stabilized crude oil at the site. As long as you do it in a managed manner, you don't exceed RVP limits, and it's acceptable to do that, and you can do it without getting significant evaporation losses. Or you can sell it as a separate product or products. You can sell it as a high vapor pressure product or fractionate it and sell it as propane and butanes. And possibly you can put in virtual pipelines, compress the gas and get it to local markets and sell it as a CNG product. And then this is just kind of the thought process that would go through a typical mitigation project. You look at what the production changes are expected to be over time, allowing for production decline. You would do your energy balances to determine how much of the waste gas stream is needed to drive any processing elements of what it is you're doing, and you also look at what the associated emissions from that would be, and you do your economic analysis to determine net present value and factor in implications of any carbon taxes, royalties, inflation, discount rates, and income tax. And when you're designing it, you would design it to consider the turndown requirements as the facility activity levels decline. So how many trains would you put in to achieve the kind of turndowns that you want? And of course, if you put in multiple chains or trains, it becomes more expensive to do that. So what is the optimum balance between trying to extract as much value from the project as you can without putting in too much capital expenditures, and then possibly looking at different carbon pricing scenarios to see how that impacts your overall economics. And when you do that, you wind up with this sort of a summary where you can identify your capital costs, your potential paybacks, net present value. Do you have enough profitable years to pay back your initial capital investment? Your return on investment expressed as a before and after tax rate of return, or as an internal rate of return. So basic things that would go into an economic analysis. I apologize, I know I've spoken longer than I probably should have, but thank you very much, and I will pass it back to you, Sunday, and to any questions that anyone has.